So we will see this in more detail. Okay? And these radicals that exit from the polymer particles to the aqueous phase, they can also re-enter again, or they can polymerize in the aqueous phase, or they can terminate in the aqueous phase. So the complexity of the process is large. Okay? So, and we want to calculate at which rate the monomer is consuming the polymer particles. So this will give us the kinetics, how fast the monomer is consumed. So to do so, we have to calculate the polymerization rate. And the polymerization rate, right there with a small case R, is like in homogeneous systems. It will be the propagation rate multiplied by the monomer concentration in the polymer particles, where the polymerization takes place, multiplied by the concentration of radicals in the polymer particles, which is where the polymerization occurs. Okay? Now, the concentration of radicals in the polymer particles, we will use to define this concentration, because this concentration depends on the number of radicals that we have in the different particles. And each particle might have a different number of radicals during the polymerization. So, since we cannot account each of the particles, because we have 10 to the 17 particles, we will use an average value. So, the total radical concentration will be calculated as you have there. I mean, like the average number of radicals per particle, which is m bar, okay, divided by the Avogadro's number to convert the radicals into moles, and divided by the volume of the particle to have the right units. So the units of this expression are mole of monomer that react per liter of particle per unit of time, second. Okay? This is the rate of polymerization per liter of particle. If you want to calculate the rate of polymerization per particle, we have to multiply this by the volume of a particle. Okay? So that the expression, okay, this is the rate of, I use R, yes. So the rate of polymerization per particle will be Kp, monomer concentration in the polymer particles, and bar. And if I multiply by the volume of the particle, now the units will be mole of monomer that react per particle per unit of time. Okay? Because this is liter of particle per particle. Right? This is the volume of a single polymer particle. And if I want to calculate the total polymerization rate, what happens in all the polymer particles, now I have to multiply this expression by the number of particles that I have. If I multiply this expression by the number of particles, I will obtain an expression that you will see in books and in articles, which is A bar. Now I have to multiply by the number of particles divided by Avogadro. And the units now are mole of monomer that react per unit of time. If the number of particles is given by liter of reactor or liter of latex, you will have also here liter of latex. Okay? But this is the expression that you have in there, and we will be now analyzing the different terms of this equation. Okay? So, a little mention about Kp. You will know everything about that. We will see monomer partitioning, how we can calculate the monomer concentration in the polymer particles, because not all the concentration of monomer is in the particles. So we have to know exactly how much monomer we have in the polymer particles. We have to calculate M bar, and we have to calculate MP. So these will be the three main topics of today. Okay? So I will start with Kp. You know Okay, I will start with Kp. This is the expression that we are using for homopolymerization. If you have a copolymerization, this Kpm is, as I mentioned yesterday, I mean, you have to develop for the two monomers, and you will have the polymerization rate for each of the monomers, which will be dependent on the propagation of a radical type A with the monomer, or a radical type B with the monomer that you are considering. So you will have two equations, one for A and one for B. Okay? So you need to take into account that monomer I will react with rowing chains terminated in A and rowing chains terminated in B. So the expression is the same, and so that you know from the copolymerization kinetics. Okay? Now here the term that appears is, I guess that you know this expression is the probability or the fraction of having a radical terminated in A or terminated in B, and this is obtained from the pseudo-steady state balance of the growing radicals. Okay? So I don't want to spend much time with this, but we have an equilibrium all the time in a copolymerization. We have radicals terminated in A that will, by reacting with monomer B, become B, or radicals terminated in B by reacting with A will become B. So this, from this equilibrium, you can calculate this probability. Okay? And the probability is defined by the concentration of radicals of type A divided by the total concentration of radicals. Okay? So this is, I guess that you know this from homogeneous systems. Okay, and now we will enter into the topic that I'm more interested to show you, which is more specific of emulsion polymerization, which is the calculation of the average number of radicals per particle. So the average number of radicals per particle depends on three mechanisms. On the one hand, the entry, which is the rate by which radicals that are generated in the aqueous space enter into the polymer. Second, what is the rate that the radicals that are growing here exit to the aqueous space, and also the rate at which the radicals that are growing here terminate. So these three mechanisms will control which is the average number of radicals per particle. Here you have the entry, exit, and termination. Okay? So let's see qualitatively how does this, the values of the rate of entry, exit affect on the average number of radicals per particle on the polymerization rate and in the molecular rates. For instance, if we analyze the polymerization rate, if we are in a system and the radical entry increases, what will happen is that if the radical entry increases and exit and termination remains the same, the average number of radicals per particle will increase. We will have more radicals as average. Okay? And therefore, according to this equation, if this increases, polymerization rate will increase. Now, if the exit increases, the rest be the same, M1 will decrease because we will have more exit, there will be less radicals inside, and polymerization rate will decrease. Okay? With respect to the molar masses, if entry increases, if the frequency of entry increases, there will be more termination, and therefore the change will be shorter. This is what we were speaking yesterday. If radicals enter at a higher frequency, they will terminate, and the radical will have less time to grow, so that molecular weights decrease. If the rate of exit increases, it's not clear what will happen with the molar masses. Okay? Because for the rate of entry to increase, as we will see now, we need to have transfer reactions in the polymer particles. And transfer reactions cut the molar masses. So we will see now this in a little bit more detail. Okay, so what we will do now is to analyze the mechanisms for entry and exit. Briefly, I don't want to enter in lots of details, but I will give you the references where you can take into account this. So radical entry. To simplify the problem, we are considering a single particle with the electrical double layer, which is surrounding the polymer particle, so where the counterions of the charges that we have on the surface are located, and a surface active radical. Okay? So entry will occur if this radical enters into the polymer part. But first we have to form this radical, which is surface active. So that means that a radical to be entered has to have, as we discussed yesterday, a few monomer units that make this surface active. Okay? So from here we have to reach here. In between we might have termination reactions. Not all the radicals will reach to this size. Okay? So that only some radicals will enter. This radical will not enter. Okay? Because it's hydrophilic enough as not to be surface active. Okay? And in the way, we have other radicals which are not surface active either. So we are considering that this is a surface active radical. Now, this radical to enter here should overcome this distance there. So there are different ways of modeling this. Okay? Some researchers have modeled this using a collision mechanism. Others have used aggregation. Others have considered propagational. But the most accepted mechanism is diffusional mechanism. So that the radical diffuses through this electrical double layer, so this aqueous phase, then in the heavy layer, and then in the polymer. So this radical has to diffuse here, then diffuse in the heavy layer, and then diffuse in the polymer particles. Each step is a resistance to diffusion, or a resistance to entering into the polymer particles. Okay? So these resistances can be modeled. So in general, what it is done is to assume that the rate of entry, which is dependent on the length of the radical, so that's why it's length dependent. Here, rate of entry depends on J, which is the length of the radical, so the number of monomer units of the radical, is equal to an absorption coefficient that depends on J, and the concentration of this size of radicals in the aqueous phase, where the absorption coefficient is given by the three resistances that we mentioned. Okay? So these three resistances can be modeled. Okay? I will not enter into this because we don't have time, but if someone is interested to know how these values of R can be calculated, these two references are appropriate. Just to show you some experimental results in which this dependence on the, for instance, the surface charge is important in the polymerization rate or in the calculation of M bar. So these are two experiments done by these researchers in which they use seed polymerization with the same seed, the same particle size of the seed, but the particles have different charge density. Ones have little charge in the surface, others has a lot of charge. So what they observed is that when the charge in the surface was lower, the polymerization rate was higher than when the charge was high. So basically this is implying that this resistance was changed from one case to the other, and when there is a lot of resistance here, the entry of radicals was lower, and therefore the average concentration of radicals was lower and polymerization rate was lower. This is what they found. Okay. The other aspect that is important for entry is the solubility, or let's say, the solubility of the monomer. Here you have two case examples: vinyl acetate and styrene. Styrene monomer has a very low solubility, 10 to the minus 4 grams per 100 grams of water, whereas vinyl acetate has high solubility, 2.5 grams per 100 grams of water. This means that when you are running an emulsion polymerization with styrene, the concentration of styrene in the aqueous phase is very, very low. When you have vinyl acetate, the concentration is much higher because of the solubility. So this means that the polymerization rate in the aqueous phase with the styrene for this addition will be really slow, because the concentration of monomer in the aqueous phase this will be very low for styrene and high for vinyl acetate. So this means that this will go slowly. So the addition of monomer units in the styrene polymerization will go slowly. For vinyl acetate will go fast. Okay? So, but there is an additional difference, and is that each time that we add to the radical an styrene unit, this oligo-radical now changes the hydrophilicity a lot, because styrene is very hydrophobic. So it's enough to add 2 styrene units to have something which is already very surface active, so that can enter into the polymer particles. In the case of vinyl acetate, each time that we add a monomer unit, the solubility of the oligo-radical changes very little. So we need to add a lot of units of vinyl acetate to be able to have something which is surface active. So the conclusion is that the entry of radicals depends also on the rate of formation of the surface active radicals. Okay? So here you will have plenty of sizes that can enter. Here, in which you have 2, they will enter to the polymer particles. Whereas with vinyl acetate, you will have plenty of sizes that can enter, but they have much more time to terminate also in the aqueous phase. So this is why when you run polymerization with vinyl acetate, you might have plenty of water-soluble material, because radicals are growing and terminating the aqueous phase before they enter into the polymer particles. Okay? So the general conclusion for radical entry is that short oligomers with hydrophilic end groups do not enter. They need to grow until being surface active. Oligoradicals of different lengths contribute to the entry, as we see for the vinyl acetate. And the general model is too complicated. So normally, what we do when modeling entry is to assume that the entry rate as an absorption coefficient without dependence on the length multiplied by the total radical concentration. So this is what it is normally accepted. Okay? Or is used because it's much easier. Okay, now the other mechanism that controls the average number of radicals of the particle, which is the exit or the distortion. You will see also in some papers like distortion of radicals. So, distortion or exit of radicals occurs only for certain radicals. Not all the radicals can exit. In the polymer particle, we will have growing radicals with different sizes. Not all exit. Why? Because the polymer radical here will be sufficiently long. It won't be like in the aqueous phase that they are still very low, because the polymerization rate is too slow in the aqueous phase, because the concentrations are very low. Here, monomer concentration is very high. Okay, because we have only monomer, basically, monomer and polymer. So monomer concentration is high, so here the chains will grow fast. So the only radicals that are assumed that are able to exit are monomeric radicals, short radicals. So for short radicals to be formed, you need to have chain transfer mechanisms. So a long radical you will have a long radical. If it finds monomer, which is normal, you will have a dead chain and a monomeric radical. So this is saturated, the chain is saturated because abstracts a hydrogen from the monomer, and you get a monomeric radical. The same can happen if you have chain transfer agent. If you have chain transfer agent, what you will have is the dead chain, but you will have a radical in the chain transfer that can continue. And this is also a small molecule that can exit. Okay? So, therefore, to have exit, we need first to calculate the rate of formation of these monomeric or short radicals. Okay? These radicals now can exit because they are small, the diffusion is fast or can be fast. Okay? Much faster than the diffusion of this radical. Okay, that's why we don't consider that this exit, because his diffusion is very slow and it terminates before it can exit. Okay? But this one moves fast because it's small and can exit, but it can also propagate here. So you will have to compete, you will have to take into account which is the probability that this monomeric radical exits. So that the rate of exit will be the rate of formation multiplied by the probability of diffusion, which is the rate of radical diffusion divided by the rate of propagation, because it's the main mechanism, it's the fastest mechanism. So once the radical exits, taking into account these two folds, this radical can also re-enter to this particle or to other particles surrounding them. Okay? So which means that to calculate the net rate of exit, we have to account also for the probability of re-entry. And the probability of re-entry will be proportional to the rate of entry, the diffusion again, divided by the other possibilities that the radical has in the aqueous phase, which are propagation and termination. Okay? So this rate, these terms, are normally expressed by a distortion or exit coefficient multiplied by the average number of radicals multiplied by the number of particles. Okay? The KD, like before for the KA, can be calculated. I will not take me. You have here a reference where you can follow the description of how the distortion coefficient is calculated. Okay? But the distortion coefficient depends on this gamma, which is the rate of transfer to monomer, depends on the propagation, on the partitioning. So there are all of these terms that I put there, but I think that the concept that you should take into account is that not all the radicals in the polymer particle can be solved, only monomeric radicals can exit, and that this exit should be considering taking into account also that the radicals can leave. Okay? So taking into account these considerations, you have a distortion coefficient that can be calculated in each case. Okay? So with this we have already defined the two mechanisms. Okay, this is a summary. And now we will analyze how to account for the average number of radicals per particle. Okay, the concept of the average number of radicals per particle is what I explained before. In the polymerization we have 10 to the 17, 10 to the 18 number of particles. In each particle we have different mechanisms. So each particle has a different history on the number of radicals. In this one we have entry, the number increases, then we have termination, then we don't have anything, then we have again exit. So each radical will have, or each particle will have different number of particles along the reaction. So accounting one by one is impossible. So what we do is we make a representative particle of all of them, and we calculate the average number of radicals per particle, which mathematically is this. Mathematically, this is the total number of radicals divided by the total number of particles. The total number of radicals is summation of n multiplied by nn, when nn is the number of particles with n radicals. Okay? So we have n0, n1, n2, n3, so number of particles with different number of radicals. Okay? If I sum all of them, I have the total number of radicals in all the particles. And the summation if I divide this by the summation of Mn, this summation is Mp, is the total number of particles that I have. Okay? Divided in different number of radicals in the particle. Okay? So this is what we have to calculate, or what we have to solve to calculate N bar. Okay? So this implies that we will have to do population balances for the particles with N radicals. Okay? To do the population balances, so we will have to write population balances for these particles, and the population balances will be just the rate of generation of particles with N radicals minus the rate of disappearance. Okay? And the rate of generation and the rate of disappearance of these particles depends on these three mechanisms: the entry, exit, and termination. Okay? So, before going to the balance, the rate of entry, we will express the rate of entry in second minus 1 as frequency of entry, absorption coefficient by the radical concentration in the other space, the rate of exit as a frequency of exit, like the distortion constant multiplied by the number of radicals in the particle, and the rate of termination. We will express this as this, and this might look strange for you the first time, but KT, with the rate of termination, you are used to see the rate of termination like this, no? Radical concentration squared. No? When we have two radicals terminate, the rate of termination is the termination coefficient by the radical concentration squared. If you have a radical of length n, a radical of length n, and this gives a dead chain of length n plus n, and if this is KT, so this rate of termination in a homogeneous system, you express this like this. But in emulsion polymerization, we cannot express like this. Why? Because we have, now we are calculating this in the polymer particles. The concentration of radicals in the polymer particles is very, very low. Each particle has 1, 2, 3 maximum. Okay, so that the number of radicals that you have in the particles is really small. In a homogeneous system, you have huge number of particles. Okay? Even if the concentration of radicals is of this order in a homogeneous system, in a bulk of solution polymerization, if you multiply this by Avogadro's number, the number of radicals that you have is of the order in the solution of 10 to the 16. However, in an emulsion polymerization particle, you have 1, 2, 3, not 10 to the 16. So that's why when calculating this term, we have to distinguish the radicals. And that's why here you don't have n divided by Vpn, which will be the concentration in the radicals squared. So we distinguish n and n minus 1. Okay? Because each one radical cannot terminate with itself. Here, in solution, 10 to the 16 minus 1 is equal to 10 to the 16. So there is no difference. But in emulsion polymerization, this has a strong impact. So that's why we have to do this calculation here. Okay? And then this can be, this is substituted by this C, which is used in emulsion polymerization to indicate termination. And therefore, the rate of termination in frequency units is 2Cn times n minus 1. Okay? So with this consideration now, we can do the balances now. So we can run these balances. So which is the rate of generation of particles with n radicals? Okay. Take into account that this is not a single equation. This is valid from n0 to infinity in principle. So that we have to solve a different number of equations, because we have particles with no radicals, particles with 1, particles with 2, particles with 3, and so on. Normally, we will not go infinity because we know that there are very few radicals in the polymer particles. Few numbers will be not, but we will have more than 1. Okay? This is the general term. You see here. Okay? So, the first terms are the generation, and the 3 negative ones are the rates of disappearance. So, the first step, a particle with n radicals can be formed if we have absorption in a particle with n minus 1. So, if we have particles with n minus 1 and they suffer absorption, they will become particles with n radicals. So, this is this term. If we have particles with n plus 1 and there is an exit of 1 radical, we will also form particles with n. So that's why we have this dissorption or exit rate. And if we have particles with n plus 2, if there is termination, 2 radicals disappear, so that you will also form particles with n. So these are the 3 terms that gives you the balance or the rate of formation of particles with n radicals. Now, if in any particle with n radicals we have absorption, exit, or termination, these particles will disappear. So that's why we have negative terms for the absorption, dissorption, and termination. Okay? Since these are balances for radicals, we can apply the pseudo-steady state assumption, and these differential equations become algebraic equations. So we have to solve a set of these equations to have the values of N0, N1, N2. So we will have a set of algebraic equations to be solved simultaneously to obtain the N0, N1, N2, and then from here we can calculate N bar from this equation. Okay? So the problem is that the solution of this set of equations is not easy. Okay? Several equations has been proposed. The most known one is by Ugelstad and Hansen. Okay? So they proposed an equation which is a series, so that M bar is calculated by a series of equations. It's an equation that is a series. So you have to solve the series to get the value. But a more easiest solution was proposed later by other authors. But this is an approximate solution. It's not an exact solution like the one which is a series solution. And in this solution, M bar can be calculated by this equation, where F is given by this and C is given by this. Okay? So in this equation, all are constants. The absorption constant, C, which is the termination constant, Kd, which is the distortion constant. But to calculate M bar there, which is the other term that appears, that is not a constant, so to calculate M bar, Ka, Kd, and C are constants, but we need to calculate the radical concentration in the aqueous phase. So to calculate the radical concentration in the aqueous phase, we have to do again a balance of radicals in the aqueous phase. And this is this equation that you have here. Okay? So the radicals, the balance of the radicals in the aqueous phase, to which we can also apply the pseudo-steady state, because these are transient species, is the rate of formation. Okay? How do we have radicals in the aqueous phase? Because the initiator decomposes now. So the balance, so you will have these radicals can be formed because initiator is decomposed in the aqueous phase. Because radicals exit from the particles to the aqueous phase, so because the solution of radicals multiplied for units on the Avogadro's number and the volume of the space. So these are the two positive terms. But the radicals in the aqueous phase disappear because they are absorbed to the polymer particles or because they can be terminated in the aqueous phase. So you have the negative terms of absorption of the radicals to the polymer particles and termination of the radicals in the aqueous phase. And now you see that I use this P dot square, but this is because I'm in the aqueous phase. And in the aqueous phase, the concentration of radicals is huge again. Okay, even if the concentration is very low, the number by multiplying by Avogadro's number is large. So this is again the problem before is the problem of the compartmentalization. The radicals in the particles are in lots of particles, and therefore in each particle there are very few numbers. Okay, so as I said, this is also a transient species. We can apply simple steady state, and we have an algebraic equation. So we have to solve, to calculate M bar, we have to solve this equation together with this one. But here, someone has been fast, quick enough, has to realize that to calculate this, we need M bar. So we have a problem. To calculate M bar, we need P dot. To calculate P dot from this algebraic equation, we need M bar. So the only way to solve this is to do an iteration. Okay? So normally you iterate assuming, so you assume M bar, take a value. With M bar, you come to this equation where everything is known, or a coefficient that you should know, and you calculate P dot. As a third step, with the P dot, you go now to this equation, you calculate M bar, in the fourth step, so this is calculated. Now you compare if M bar calculated and M bar assumed are equal. If they are equal, you are a genius, if you do it for the first time. But if you are not, you come back, and in few iterations, you will get the two solutions, M bar and the radical concentration in the aqueous phase. Okay? So this is a way. And now, I think this is the graphical solution of the solution proposed by Ugelstad. Okay? So, and this is obtained, this solution, this graphical solution, which is very intuitive to see, is obtained from this equation basically, making these terms non-dimensional. Okay? Making them adimensional. Dividing each term by the rate of termination multiplied by the number of particles, you make these terms non-dimensional. And this is what they plot in this graph. So, let me explain you a little bit. In this graph, which is a graphical solution to calculate M, right? What they are plotting in this graph is the log of M bar versus the log, is a double logarithmic of alpha to beta. Okay? So, M bar, we know what it is, M bar. This is this term, which is basically this rate of generation of radicals in the aqueous phase divided by C times NP. Okay? This term is okay. It somehow takes into account the rate of generation of the radicals in the aqueous phase divided by the rate of termination. Okay? The second parameter that they use in the graph is M. N is KD divided by C. And this is obtained by dividing this by C and P also, okay? With adjusting the Avogadro's number and the volume of the aerosols, okay? But this now, this N value is a ratio between the rate of exit with respect to the rate of termination inside of the polymer particles. And the last term that they use in the plots is Y. And Y is, again, this term divided by C and P and adjusting a few values, okay? And this is this Y, which is KT in the aqueous phase, C and A divided by K squared P, okay? This takes into account the probability of the radicals to terminate in the aqueous phase. How important is the termination of the radicals in the aqueous phase, okay? So these are the three parameters that basically control the average number of radicals in this equation. So this is the solution, and here now what you have is M1 as a function of alpha for different values of n and for a single case which is no termination of radicals in the aqueous phase. So the radicals do not terminate in the aqueous phase because Y is 0. Okay? So this is a case which is very classical for instance, very hydrophobic monomer, style. Not for binding acetate. For binding acetate, termination in the aqueous phase will be important, as we have seen. But for styrene, this holds very well. Styrene and hydrophobic monomers. Okay, so now you have M bar, alpha, and N. So, and you can distinguish three different regions in this graph. The region, okay, this value, the log of M bar 0 is here. This value is what corresponds to a value of the log of M bar of minus 0.4, which the inverse of that is M bar equal to 0.5. So that this line here, with N is 0, this line is M bar 0.5. So this line that we have there corresponds to M bar 0.5. Below this line, M bar is much lower than 0.5. And above this line, M bar is higher than 0.5. Okay? So, if we take this area first, the area in red, what we see is that different values of M increasing, this is 10 to the minus 6, 10 to the minus 5, 10 to the 10 to the 2. So M is this. If N is lower than 1, okay, when N is 0, which is this line, means that we don't have exit of radicals. KD is negligible with respect to C, to N is 0. Okay? When N increases, that means that exit starts to compete with termination of the polymer particles, termination of radicals in the polymer particles. Okay? So what you see is that if M increases, desorption increases, the value, the lines go to lower values, so that M bar decreases. Okay? When M is important, when desorption is important, the number of radicals per particle is below 0.5, well below 0.5. Okay? And this occurs in a large range of values of radical concentration, okay, in the aqueous phase. Now, if N is 0, so desorption is negligible, we don't have exit of radicals, so that the radicals enter and terminate, but they do not exit. We are again in a large region of alpha values that M bar will be 0.5. So and this is the ideal case of emulsion polymerization. So that half of the particles will have a radical, half of the particles will have 0. Okay? 0-1 system. Particles with 0 and particles with 1. So this is a very special case, but this is the ideal case for emulsion polymerization, because this is where you will have the good control of what I was saying yesterday that was unique in emulsion polymerization. The case in which molar masses and polymerization rate can be increased simultaneously. Because this is where the system will be fully compartmentalized. Okay? We have particles with 0, particles with 1. If we have a particle with 1 and a radical enters, instantaneous termination. Particle with 0, and here another one enters. So we will have 0, 1, 0, 1. The average 0.5. Okay? And under these situations, you have the unique properties of emulsion polymerization. The third case, in the third case, you see that all the graphs together, here, no matter which n value, it doesn't matter if I have exit or not, the values of n bar will be above 0.5. Okay? So this is what it's called pseudo-bulk system. So we will have particles with plenty of radicals, and the kinetics will be like in the bulk or a homogeneous system. Okay? And this occurs when you have, no matter which n, a lot of or high values of alpha, which means high generation of radicals or low termination of radicals in the polymer particle, or a large or small number of polymer particles. Okay? This to be large, this has to be large, or this has to be small. Okay? So this occurs in situations where alpha W is high. Okay? High concentration of radicals, or low number of particles, or very low termination of radicals in the polymer particles, to have plenty of radicals in the polymer particles, and the situation will be like in a suspension polymerization. Okay? But with smaller particles. Okay, and to finish this part, in which experimental conditions we are in the different regions. By the way, I didn't say that these three regions were the regions that in the 48 Smith and Ewart identified qualitatively. Okay? So they define like region case 1, Smith Ewart is where n bar is below 0.5, Smith Ewart case 2 is n bar equal to 0.5, and Smith Ewart case 3 is n bar is higher than 0.5. Kubelstadt and Hansen were able to do this with quantitative equations. Okay? So, n bar below 0.5. We need very small particles, below 100 nanometers, very water-soluble monomers because we need distortion. So to have distortion, we need small particles, to have fast diffusion, water-soluble monomers that would like to go out, a small amount of initiator, we are in this area, so that this should be small, and or LP very high. But this is related with the number of particles. If the number of particles, if the size of the particles is small, we will have a lot of number of particles. Case 2, this is the case that we are interested in. To be in this area, because this is the specific or unique emulsion polymerization. Here we need water-insoluble monomers, like styrene, to have negligible distortion of exit, Kd equals 0, M0. Okay? No chain transfer reaction, so we need monomers that do not suffer chain transfer reaction, or we don't have to use chain transfer agents, because otherwise we will have radicals that can be dissolved from the polymer particles. We need, alternatively, rapid termination, C high, to have M small. And particles not much higher than 200 nanometers, because otherwise we might enter into this region. And case 3 is achieved when we use very large particles. So with large particles it will be easier to have more radicals in the polymer particles. In the small ones it's difficult because termination will be faster. High amount of initiator, but normally redox systems, because we need alpha W which is high, so we need high generation of radicals. Or we need also slow termination rates, and this occurs when you have gel effect. So if you have monomers like NMA that suffer gel effect, you can have a decrease in the KTs, and you will be also in this pseudo-bulk region. Okay? So with this, I finish the first part, and we'll make a break now. 10 minutes, 15 minutes, and then we continue with the last tutorial.